So let's continue with diffraction by method number 2. This is the method where we use the pinhole. Here on the left we have our waves which are emanating from the laser. We have the pinhole, the slit here is the pinhole, and over here on the right we have our screen. On our screen we saw the concentric circles of dark and white rings, and using this formula down here on the bottom, everything is known except the diameter of the pinhole. We know the wavelength of the laser, we know the distance between the pinhole and the screen, and we can also measure the distance between two adjacent dark rings. This is the setup, again showing the distance Z and where the aperture is and where the screen is. By the way, we call this the Fraunhofer diffraction pattern. So here are the parameters that we'll use in the formula, and the formula will enable us to find the diameter of the pinhole. So to create this pinhole diffraction pattern in the lab, you can use a laser pointer, cover it with aluminum foil, then with a very fine sewing needle puncture a clear small hole in the center of the aluminum foil, and then shine a laser beam into the hole and allow the light to escape onto a white screen. We can use the measurements to calculate the diameter of the needle. And again, here's the formula. The measurements that we took are shown here. The distance between the pinhole and the screen was 11.52 meters. The wavelength of our laser was 532 nanometers, the green laser pointer, and then the radius of the airy disk in our case was 12 millimeters. Plugging everything into this formula, making sure that we use the right units, converting nanometers to meters and also millimeters to meters, and executing this formula, we came up with a diameter of 623 micrometers, and that compares very well with the diameter of the needle, which has been measured with a micrometer, 650 micrometers.